Hey everybody, welcome back to day 5 in this series, Advent of Code 2023, where today we're having a look at some gardening related problems. So day 5 is titled If You Give a Seed a Fertilizer, which I think is a pun on that if you give a man a fish thingo, but we won't read too much into that. The problem for today is to take at least for part 1, take a list of seeds, which are listed at the top of this sample input file, and map them through a series of stages to ultimately get to a location. So the way we do this is we get these maps, which are like tables that have a title row and then a number of different rows. And each of these rows can be interpreted this way. So the first number is the destination. So in this case, it'll be soil. The second number is the source, which would be the seed. And the third number is a range. And what this first row is saying is that seeds, starting at seed 98 and for a range of 2, so 98, 99, you should map seeds to soils starting at 50. So 98 becomes 50, 99 becomes 51. The second row, very similar, 50 becomes 52, and then 51 becomes 53, and so on for a total of 48 entries. And the rule is that if we don't have an entry that maps, let's say we get seed number 6000, that just maps 1-to-1. So it'll become soil number 6000. Our job is to take the list of seeds that they give us, map them through each one of these stages all the way through to a location, and report back with the lowest location in amongst all the seeds that we're given. And then spoilers, as always, the answer in this case was 535088217. But let's take a little time now and see how we got there. So we're here in day5.rs, our Rust file, and we'll start from the top. We got 2 structures that we define as part of this problem. We have one called range map, which is just a structure to store each line of those maps that we saw before. So it's got the source starting point, the destination starting point, and the range. Pretty simple. We then have another structure called a tree dest, which is 2 pieces of information. It's the destination, hence dest, which is the output of the map. So in that first one, seed to soil, dest would be soil. And then we have a structure called an interval tree. Now, an interval tree is a tree, believe it or not. It's a data structure that is really well optimized to finding the overlapping points between intervals. So you can think of intervals as a sequence of numbers. It might be a sequence of times or date ranges is pretty common for interval trees. And we want to be able to run the query and say, hey, I've got some interval A to B. Can you tell me within all the intervals in the tree where any overlaps are? And for those given overlaps, the benefit of this particular form of interval tree is, can you return the data stored against that interval or that overlapping span? And you'll see why that's useful later. Strictly speaking, it's only really needed for part 2, but you'll see in this problem, part 2 really makes us rethink the whole implementation here, which is why it exists. So diving into the code itself, starting right up the top here of day 5, we have 2 storage areas for our data. We have a vector of seeds, which are those seeds that they give us at the top of the file. And then we have a collection of tree dest structures in a hash map where the key is a string, which is the source. So the first one, seed to soil, the key will be seed. And then for the next one, which is, I think, soil to fertilizer, the key will be soil. That allows us to quickly look up the mapping data to move from one category to the next. As per usual at this point, we then read in the file contents into a string and get ready to start parsing it. Now the parsing step here, we start by defining a few variables to help us move through the parsing step. One, to determine whether we're currently in the midst of reading in one of those maps. A placeholder for our source and destination values, and an interval tree, an empty interval tree to store all our information into. We then loop through the line, through the contents, I should say, line by line. If the line's empty and we were previously parsing a map, we then say, all right, we're done with that map. We've reached the end of it. And we put it into our maps structure, keyed by the source, as we said, with the tree dest as the value there. And we also say we're done being in map mode and we go back to being in not map mode. There's only really two states in this state machine of parsing. We then continue to the next line. Now, if we weren't in map mode, we check whether the line starts with two key things. It can start with seeds, in which case we're right up the top of the file, and we parse the seeds. We replace seeds : space with nothing, split it around its spaces, and read each of the results in as a 64-bit integer, pop them in a vector. Pretty simple parsing for that one. If we see the word map at the start of our string, we switch into map mode. We use a regex here, which maps characters A to Z into a value source, then -2-, and then characters A to Z again into a variable called dest, and then map. We do this to quickly extract the left and right side of, say, seed to soil, and so on, so that we can store that for the various keys in our data structures. We then check that we did get some matches there, a little bit of error handling here, just in case we didn't. Then we extract the source and the destination into our temporary variables, and we create a new empty interval tree. And then, again, we would continue on our way. Now, if we were in map mode, we then parse each line as 3 integers: destination start, source start, and range, again using a regex. We capture each of those. We capture the lower source, the range, and then within here, the lower destination. The reason we do these other two outside is because we need them for the mappings data structure. But really, we probably should have put destination start in its own variable too to keep things nice and clean. But we parse those as numbers, and we build two things. We build a range map that mentions the source, the destination, and the range, and then we insert it into our interval tree. As I said before, interval trees, they're keyed on intervals. In this case, the interval between the lower number, so 50, and the lower number plus the range. So 50 to 52 stores this map as the data. So by this stage, we are finished with the parsing. We have a collection of interval trees keyed by their source, and with some additional information about how to map data from one category to the next. Now we're going to jump down here a little bit. This is all code for part 2, which we'll come back to. And we'll have a look at this loop here. What this loop does is it loops through all the seeds that we're given, takes them through all the stages between seed and location, checks if we found a value that's lower than a value that we've seen before for location, and if we do, we store it. So pretty simple here. We loop through the seeds. We start off at the seed stage. We start off with a seed value. So that's just the number that we're given. And then we loop through until we hit location as our current stage. We use our hash map to get the current mapping function based on the current stage that we're in. We then take note of what the destination stage is after this one, and then we attempt to find overlaps in our interval tree. Now, in my original Part A implementation, I didn't have an interval tree here. We just looked through the values themselves. We didn't need it because we were mapping a single value through. And you can see here, when we're doing our find function, the range that we're doing find on is current value to current value plus 1. And because it is not inclusive of the upper bound, that's really just a single value range. But it works just as well here. So what can happen here is, one, we can get no matches. So, as I said before, seed 6000 didn't have any matches in that previous example. In that case, we won't go into this loop. We'll move on to the next stage, and current value, which we set up here, will remain the same. The second thing that can happen based on the way that the data is structured is we can have exactly one match because we're comparing one value to a series of ranges. If we do have that match, We grab the data for that interval that we match to. We do a bounds check here. This is a hangover from the previous implementation, so it's not strictly needed, but we do it anyway. And then we map into current value the lower start of the destination plus how far through we were through the range. And that updates our current value. This process continues until we hit the location stage. And then outside of that loop, we do a check. We say, look, if it's the first time we've seen anything, because min-lock was set to -1, or if this is the lowest value that we've seen so far, store that value, and then print it at the end. So pretty simple in this case. But where part 2 comes in and where this day's puzzle starts to get a little bit more complex is with the variation. Now, what this puzzle says is that we should no longer interpret our list of seeds as just, in this case, 4 seeds, but actually interpret each one as groups of 2, which represent a starting point and a range. So very similar to our map above, we need to think about the list of seeds as now a much, much bigger collection of data. And otherwise, everything is the same. We need to find the lowest location number, but now we have a lot more seeds to consider. So if we jump in here and just quickly take a look at the day 5 input text, you can see here that the values for the seeds were very big, and that was fine before because we were just moving through. But if you imagine now this is 166,491,471, that's 166 million seed values. So this suddenly becomes a problem that's very quick. We have 20 seeds. We've just got to jump through a bunch of comparisons to potentially millions upon millions upon millions of seeds that we have to check. So an iterative approach is no longer really feasible. And this is where an interval tree comes in, because it's a very effective way to compare ranges, find overlaps, and quickly process large amounts of data while really only storing the start and the end values. So it could become much, much quicker and much less memory intensive. So let's have a quick look at what we did in part B, or part 2. I call it a whole bunch of different things in here. So the first thing we got to do is we got to take that list of seeds that we had before and flip it from being a collection of seed values to a collection of seed ranges. The way we do that is pretty simply, we loop through, we enumerate. If we've got an odd number, we store that as the first value. If we've got an even number in our enumeration, we say, cool, end of the range, and we push a new interval into a collection called seed ranges. So you can see here, first time through, we'll store first. Second time through, we'll add to this interval seed ranges, first all the way through to first, plus whatever this second number is. We then do a slightly different loop. So before we looped through each range and took it from seed to location, and then we went back to seed to location 20 times. For efficiency here, what we're doing instead is we're taking each stage, exhaustively pushing all the seed ranges through it, getting a new set of intervals, and then taking that to the next stage. Turns out to be a little bit easier to comprehend as you work through it, and a little bit more useful for processing. So very similarly though, we start in the seed stage. We get our list of seed ranges. We just make a copy of it. This will be our sort of mutable variable. We'll continue to update this one. And then we do a loop until we hit the location stage. We create a new vector of intervals to store the next batch of seeds. We once again go into our maps and say, hey, give me the interval tree for the seed stage. And then we take note of what comes after seed, in this case soil. And then we loop through all of our ranges. Now remember, each one of the ranges in here is going to be an interval. Now we do call it current seeds. They're not always seeds, but it doesn't really matter. We go through and a couple of different things can happen here. So let me just try and diagram this up within the code. So if we have a range that spans from A all the way to B, and we want to compare that to some other range here that goes from C to D. if we run this against our interval tree, we're going to get a couple of different things happen. And this is our input here, A to B. All the way up to here, we're going to have one interval, which says, okay, there's no overlap. And based on the rules of our problem, we just need to map those values to the exact same values. Then we have a second interval here that starts at C and goes up to B, which overlaps with this range. And for these ones, we need to create a new interval that has the transformation applied. And you can see, depending on the size of the input range and the size of the comparison range, you may split this up a number of different ways. If instead, let's say this was a much longer range, we'd have another split here at D, and then another split here to B. And then what we might actually have here is another range that it collides with. So we just need to do a couple of bounds checks and check our interval and where it overlaps with all the other intervals in the tree, and push those new intervals into a list and continue this comparison process. Now, we could try and be smart here and re-merge the intervals after we've split them apart. If it was a huge problem, maybe there'd be some benefit there, but I didn't really find it making a difference here. Intervals are quite an efficient mechanism of storage. You're really only storing the start and the end. So let's get into that. We grab the start of our interval, our input interval, and then we look for all the matches between our interval and the interval tree. We sort those matches by the start point of their overlap so that we can process them sort of in chronological order, let's say. We then loop through those matches. Now, keep in mind that there might be no matches, in which case we just jump to the end and leave all these values as they are. But let's assume that there's a couple in here. First thing we do is we do a check. We say, is the start of the matched interval higher than wherever our current point is in our interval? If it is, we need to put that very first interval that we talked about before, A all the way up to the first match, into our list of next seeds. We don't have to do any mapping to this one because it's outside of a match. So if we get here and the matched range, or more of the range exists beyond the end of the matched range, then we need to create another interval up to the end of the match, and then update our current pointer, or our current point, to be the end of the current match. So we do the mapping with the offset, the destination start, and the length, and we push a new interval to our list, and we update our current position to be the end of the matched interval. I did have a to-do here to check for a +1 because the intervals are non-inclusive, but turns out I didn't need it. But I'll leave that there for posterity. And then the other option is that our interval matches within the matched interval, in which case we just need to push a range between here and the end of our input that has the mapping applied. We then update the current point to the end of the range. We then check, is there any room left? And if there is, after we've looped through all the potential matches, we then put the remaining chunk in unmapped or unmodified, and then we continue to the next stage, updating our seeds to be that next collection of intervals. Again, in this case, they won't be seeds, they'll be soil at this point. Once we've done all of that, we've looped through all of the different stages for all of the different intervals. We then do something very similar, where we loop through all of the different final location intervals. We look at the start points of those intervals, we find the lowest value, and then we print that out. And if we do that, then we're left with this value, 513,99228. So this was an interesting one, in my opinion, because it's the first problem in this year's problem set, or last year's problem set at this point, where the complexity and the implementation details really shifted from part 1 to part 2. It became really computationally infeasible to run the same iterative approach that you might use for part 1 to get it done quickly in part 2 because of just the sheer size of these intervals. I also like this one because it gave me a chance to use interval trees. I've known what they are for a long time. You see them in interview problems often about overlapping date ranges and things like that. But I've never had a real concrete reason to use one other than in the academic sense. So that was cool. But look, that's the end of today's video. Hope you found that interesting. If you did, please consider subscribing, leave a comment below, all that good YouTube stuff. But otherwise, I'm Elliot. I build stuff, and I'll catch you in the next one.